Okay, I stopped the last times on this slide, and if I recall, this is regarding the kinetics of rigid bodies, and the principle is to use or the kinetic energy, the principle of conservation of energy on what we have seen on particular mass point, to use the same, let's say, the same principle, not the same equations, the same principle for these rigid bodies. And for that, we have seen regarding the geometry, how to get moment of inertia for different geometry or shape, like a rectangular plate, disc, cylindrical dome, and so on. Okay, we have seen different, let's say, expression regarding the inertia sorry, there will be, I think the problem is with me. The problem is the network. It's with me. It's not with you. But it's come soon. Okay, then as I said, that the principle, the important point is for any shape or geometry, the moment of inertia has to be calculated or determined first at the center of mass. And then we can shift it or translate it or be determined on or on another or about another point. For the example here, for this circular disc or circular drum, okay, we have the if there will be such problem in the final exam, okay, I will give the value of the considered rigid body at the center of mass. And after this, you have to use the Steinert principle or equations, to shift it to the point, for example, here, or let's say for, let's say here, for the Steinert, okay, what we have seen, we have to determine first at the center of mass or gravity center, okay, and after this, either to shift it to the point A, or another. This is, we use what we call the Steiner's law or Steiner's principle, and to add the term here, we have seen how to get to this. And this is what we say, the moment of inertia about any point, it's the moment of inertia, about the center of mass plus the Steinert part, okay? And this is its only matter of geometry. Now, if we look further, as I said, we stopped here the last time. We know from the principle of angular momentum, yeah, we need the moment, yeah, or let's say the sum of the moment. And this is the principle of angular momentum, yeah. Then we have the sum of the moment, yeah. It's equal to the rate of the angular momentum. And here it's expressed by IS, which is here, yeah. That's what we have here, IS, okay, multiplied by the angular acceleration, okay. This is in, let's say, in polar coordinate system. But first, to get the moment, yeah, you know that the forces which are applied on this rigid body, that we have to make first the equilibrium of forces. And when this is the equilibrium of forces can be, yeah, used by using the D'Alembert inertia forces, okay, or in D'Alembert principle, we make the equilibrium that we know the inertia forces. When we know the inertia forces, we can calculate or determine the moment, yeah, at any point or about any point or axis, yeah. That it means that here to solve this kinetics problem for a rigid body, first of all, we use the equilibrium of forces. And this is it advantages in kinetic of mass point. Yeah. And this is we have to develop, yeah, further for kinetic of rigid body. Then we have the laws of forces and the moment about center of mass S first. This is what we do because we have the rate of the angular momentum, yeah, where we have here a moment of inertia. It's given, yeah, or it's known in on about center of mass. Then we make here the sum of the forces first, yeah, where we have here, for example, in x direction, the moment multiplied by the acceleration, yeah, and here at the center of mass. The same principle in y direction, yeah, and also in z direction if it's three-body case. And here we make additionally, yeah, we add, which is different from the particle. For the particle, we have only translation, yeah, but for the rigid body, we have what we call the rotation, yeah, and this is we have here to add this third equations for the rigid body. Then we have here the equilibrium conditions, yeah. The sum of the forces minus the here the inertia forces, yeah, must be equal to 0 in x in Y and also for the moment. Yeah. Then we said we introduce the lumbar inertial forces and the moment of inertia in this case. Then we have here Ftx, which is the inertial forces along x direction, the inertial force along center of mass. And this is the moment about the z axis. When we have here, for example, x and y, the moment should be in z direction. Then we have here the acceleration and the angular acceleration. The angular acceleration here about s, and that then about any point of the rigid body. One gets the dynamic equilibrium equation. That it means we have the sum of the forces. This corresponds to the inertia forces, and also inertial moment, let's say, and this due to the dynamic motion, okay? And this can be determined by using, for example, here, the Lambert principle. Okay, keep in mind this, and this equation are in two dimensions. In some example. These are the general equation of motion for a rigid body in plane motion or 2D, two-dimensional. Then we have here in either we have XY coordinate system or N and T normal and tangential or polar coordinate system. And this is convenient for, let's say, for circular motion, for example, system instead to use the Cartesian coordinate system. Of course, we need for the case here, I have to insist, we need the part 1 and part 2 to determine the accelerations. Okay? And for the acceleration, as we know, we have the equations, and this equations, the needed equation, let's say, I give them in the midterm, the sheet of the principal equations for the velocity and acceleration, either in n normal and tangential axis, let's say, polar coordinate system, or Cartesian coordinate system. Particles, as well as for a rigid body. Okay. Now we take this example and we try to use the previous equations. We take here the pendulum. Okay. Here we have mass, of the bar. We have seen some examples, where we had here mass point, okay, and we neglected the mass of the rod, okay. Now, opposite, what we take the rod or the bar here, which has the mass m, Now this will oscillate, with angle phi, yeah, where we have the angular velocity and angular acceleration, phi dot dot. Now what we have, yeah, the pin joint here in A allows rotation in the plane, yeah, and we try to get the equilibrium condition following the lumbar. For that, what we need? We need the external forces, okay, here, and we need what we call the inertial forces. The inertial forces, what we have here, okay, we have the force, if we use now the polar coordinate system, AR, represented by the unit vector AR and E phi, yeah, what we have here, we have the motion along phi direction, the circumferential one, and we have also the motion along the radial direction. That it means there is the acceleration or the acceleration along the radial direction, and there is the acceleration along circumferential one. One, the external force, there is the weight, yeah, mg. Then what we have to do is only to make the equilibrium along the radial direction, and we make the equilibrium along circumferential direction. What we have here as internal forces, let's say internal forces or the inertial forces or moment, we have here the forces which is opposite, that we have always the force which is opposite to the direction of the motion. Yeah, what we have? We have here the inertia forces m multiplied by the acceleration along the circumferential direction, and we have also m multiplied by the radial acceleration, AR. This is, we can call it, yeah, T or FHR, and here we can call it T phi, yeah, this one. Now we have the weight mg. Mg can be decomposed, the comp has the component along circumferential one or projected along the radial one, okay? The difference between the particle, yeah, here we have the moment, okay? And this moment here, inertial moment, is expressed by the rate of the angular momentum, which is is multiplied by phi dot dot, okay? Now, if we make the equilibrium, what we have? We make the equilibrium about the point, for example, here, A. We have here the reactions, which are AR and FE, yeah, as it rotates about this point A, yeah, that it means there is no moment here at the point A, yeah. Then what we have here the radial one along AR, that it means the reaction in radial direction, AR, and here minus MAR plus MG. The second one, okay, we have the same principle, A phi, and we have minus here MEV, the inertial forces along the circumferential direction. And we have also minus mg sine phi. And this is equal to 0. Now the third one, we make the sum of the moment about A, yeah, is equal to 0. In this case, we have here this moment, yeah, which is opposite to the z-axis, okay, in negative direction, yeah. This is inward. Then we have is phi dot dot, okay. And additionally now, we have this force here, mg sine phi, okay, make moment about this point A, yeah, as conferential one, yeah, make also moment or induce moment about the point A. Here, the radial inertial force as well as the projection of the weight along the radial one make no moment, yeah, induce no moment as, yeah, it's along the axis AR. Yeah, there is no, let's say, arm. Then we have here minus MEV. This is this force, and we make here the arm, it's only L divided by 2. The same for the arm also here, it will be L divided by 2. L divided by 2 because it's the center of mass, yeah. It's at the distance of L divided by 2. Okay. As I said, you have here in red the inertial forces as well as the inertial moment. Yeah, this is what motion. Now, what we know, we have ER here, the acceleration along the radial one and the circumferential one. You remember, or I give you already the formula. Yeah, in expression, it's for the radial one, it's only omega cross the position vector r. In our case, r, it's only L divided by 2. Circumferential one is defined also by omega dot cross r. Yeah. Omega dot is only phi dot dot, okay, and r stay L divided by 2. Now we can get from the equations first the reaction AR, okay, and the reaction along phi direction. We have a phi here, it's given by this equation here. Now for the third one, then we have the dynamic equilibrium of moment. Yeah, what we have here, we have when we take ES here, that is means we take here mg sine phi L divided by 2, okay, and MEV we have to replace it, and we see this is, it's only IS, that is means the inertia of moment, yeah, IS at the center of mass plus the Steinert part, okay, and this is will be IA, yeah, inertia of moment about the point A. Yeah. And this is when we do it that we have here 1/3 ml square. Okay. Now, if we make here a vibration differential equation, what we have, we are on place here, yeah. What we have phi dot dot, and we have phi here. If we make, let's say, linearization or small phi, we have sine phi, which is equal to phi, okay? Then we get here this equation, and where the 3/2 multiplied by G divided by L, it's only the eigenfrequency, which is omega square here. And this is, we have seen it, yeah, is the same example as we have seen it, yeah, in the part here 2.7 or chapter 2.7, yeah. Now, also that with the solution of the equation of motion, that is means if we make now the solution, which is phi, it's equal a cosine omega t plus b cosine omega t. Yeah, when we get the A and B with the initial condition, also, yeah, can be determine the forces, yeah. The reaction forces or the support reaction forces can also be determined. Now, we have seen this in 2D or in plane problem. Now we look to the kinetic of a rigid body, yeah, in 3 dimension, yeah. What we have here, the fundamental relations developed for the plane motion of a rigid body may also be applied to the general motion of three-dimensional bodies. It's only we have to choose, yeah, the let's say the right equations. This part is concerned with the evaluation of the angular momentum, okay, and its rate of change for, yes, okay, and its rate of change for three-dimensional motion. Now what we have here, we have the forces which are applied on the body. We have the center of mass, okay. This is will be equivalent to take the resultant of all forces, but these forces, yeah, have different directions. That it means if the force is not through the center of mass, if it's not the case, this force will induce moment. Then it means this system here, it's equivalent or equal to this system where we have, yeah, the resultant of the all forces plus, yeah, the moment. The resultant pass through the center of mass, and the moment also has to be determined about the center of mass or gravity center. Okay, then it means here the equation of motion about mass. Okay, there is some times problem with connection or the network, but it's only, yeah, maximally 1 second, yeah. But the things will work normally after this. Okay, then we said that the equation of motion, we have to determine, yeah, to make the equilibrium of the forces as we have done it for the pendulum of the let's say beam or the pendulum of the beam, or let's say thin bar. Here we have to make the equilibrium, the mass, and additionally, we have here the moment, which is only the rate or the time derivation of the angular momentum, yeah, and this is can be generalized here, where we have here delta r dot, it's only omega cross delta r. Then if we generalize this equation, what we have is, and this angular momentum